Hi, I'm Ed Sperling. I'm the editorial director of Low Power High Performance Engineering. I'm here with Mark Throndson and Sudhakar from MIPS. We used to have one core and an SoC, but as we move down the Moore's Law roadmap, it's impossible to do that simply because there's too much heat. So can we, as we start adding more and more cores, can we actually use all those cores?
Actually, there's people talking about the death of Moore's Law, and we're probably a bit premature on that, but it definitely big challenges in getting scaling on frequency and power in particular as we migrate on the process technology side. So I think what it says is that you need to be able to make more efficient use of silicon technology, and it probably starts with architectures. A pure RISC architecture can deliver very efficient performance, and that's frankly that's what MIPS is all about, and so it starts there, and I think then you need to look at the various parallel processing technologies and implementation technologies to make better use of the silicon at a given point in time.
One of the consequences of the slowing down of Moore's Law is that we need to build a wider portfolio of processor cores. It's no longer going to be true that one single processor architecture can deliver the same high performance and low power in one package. So we will have to intelligently use a variety of processor cores to build systems that meet the requirements of the market.
But we've been hearing to some extent about the benefits of multi-core for many years. We've dealt with this back in the old days of symmetrical multiprocessing. We've still never been able to take advantage of that for most applications. You can do it in commercial, but not really on a lot of the consumer applications.
Right.
Are we making any progress there? Will things change?
Yeah, I think you stated it in terms of it works in some markets and not quite as well in others, and I think we'd agree with that. We see a very large amount of scaling in networking and storage and automotive and image processing type applications, but at a more limited level in terms of the consumer space. So I think again it comes to needing to emphasize delivering more performance per core and using technologies that actually help you deliver the right amount of performance at the right amount of time and scale performance and power according to the workloads. So this is all about having very effective power management techniques coupled with hardware technology that lets you make use of those, as well as heterogeneous processing as a scalable element.
Software today is one of the biggest power hogs. What can we do about that, and are we making any progress?
Well, I think we're making progress, but it's obviously going a lot slower than we would all like. One of the key things that we see at MIPS is that the hardware actually offers a lot of features to enable software to reduce power, and for each processor there is an optimum point at which it needs to be operated for the task at hand. And software has come a long way with techniques like DVFS, or dynamic voltage and frequency scaling, but it's still not pervasive because A, it's not standardized, and B, the level of cooperation between software and hardware is still something that we're all working on. So certainly there's a lot of truth to that, but I think necessity is the mother of invention. So as these power problems become more challenging, I think we will all step up to that challenge.
So yeah, I think you hit the nail on the head. I think the underlying technologies are in place, but whether they're being used as efficiently and fully is really the challenge in marrying the software with the hardware and
right.
Taking full advantage of the capabilities.
And we do see that there are systems which are very, very power limited and energy limited. The mobile computing space is the prime example, and simply in these new markets, the software ecosystem is not as mature as it is on, say, the desktop world. So it will take some time for those techniques and that awareness to filter down to these levels.
We're also hearing a lot more these days about the possibility of many cores that are very specialized. So you may have a processor that's good for video, and another one that's good for audio, and another one that's good for something else. What does that mean for MIPS?
Actually, I think it's an interesting question because, and I think there's a place for both technologies. There's obviously huge amounts of software involved in these solutions today. One thing I like to say is that, ISA, instruction set architecture, equals ecosystem. And the more disparate components that you have in the system, the more difficult it is to create the overall ecosystem needed for a solution. So, but at the same time, there's no one product or processor that can satisfy all problems effectively. So I think there's room for both technologies.
Right. And I would say, add to that, Mark, that about once a decade somebody comes along and says that specialized processor cores are the answer. So in the 1960s it was systolic arrays, in the 1970s it was something else, and today there's all this talk of dark silicon and so on. But you have to realize that the proven paradigm of a general purpose processor core, which can handle almost any task you throw at it, is definitely here to stay. And over the last 30 years, the rate of shipments of mobile processors and every other kind of processor just shows no signs of letting up. So if you look at it from that viewpoint, each additional processor that gets sold broadens this ecosystem that you're talking about, and that in turn sets up an incentive to design more software for it, so it becomes a very virtuous cycle. It's very hard for a specialized core to bootstrap itself unless it can fulfill a wide range of applications. And we simply haven't seen that. We are not saying that it can't happen, right? And we are not, we believe in specialized cores because there are things like a graphics processing unit, which the general purpose processor core would be ill-advised to undertake. But that's why we see that there's room for both. But back to what I said, if you have a portfolio of processor cores, you can pretty much cover the spectrum of needs for the foreseeable future.
One of the problems with having many cores on a chip is also that you have to maintain coherency between them too. Is that correct? What do you do about that? Because there's an impact on both performance and potentially even on power if you have too much coherency.
True, absolutely. So we do spend a lot of time and effort to thinking about and tackling that problem. But in the sort of systems that tend to be very power limited or challenged for energy consumption, the mobile market, for example, is not ever going to go to a very large number of cores, right? We see today between 2 cores and 4 cores as being the sweet spot. And just like we had in the PC world, it never really gets up to something like 8 cores. So would you say, Mark, that in this domain that the challenges of coherency are reasonably well understood?
Yeah, at least in terms of the homogeneous processing aspect, but I think there's also the heterogeneous processing aspect, and so so there's more processors in the system. There's a GPU, there's other components for security and things like that in many cases are implemented on separate cores, potentially running a separate operating system. So you have to ask the question in each case, how important is data coherency across all these different processing structures?
And to add to that, if you obviously look at the problem domain of supercomputers, where you have a massive number of processors, always had and always will, the software itself kicks in and is designed so that you do not need cache coherency on a large scale. So that, to your previous question, that's one area where the software does keep up with the hardware because people are willing to pay a lot of money for it. And there's simply no other alternative.
Globally, are we starting to see more demand for higher performance? Is that a universal thing? And if so, what does it mean by, is there a difference by region?
Yeah, I think there's always a pull up and to the right in terms of performance, but we do see that it's bifurcating a little bit based on geographic sector.
Yeah, it's driven by the revolution of the web-connected consumer device. Whether you're talking, phones, tablets, TVs, set-top boxes, the internet revolution, the idea of being able to access content on any device at anywhere in any place really is pervasive to these devices. And the user experience required to make that, or to make that user experience exciting, demands very significant levels of performance. So the interesting part of that is that regardless of what geography we're talking about, pretty much all the device manufacturers have a common goal. They're just taking different approaches to getting there. Some are using more cost-optimized technologies and pushing very hard on the implementation within that technology. That's typically what we see with a lot of our customers in the Asia area, whereas in some of the other regions of the world, they might be choosing the absolute highest performance processor first and foremost, and trying to push the technology that way in more advanced nodes.
Right.
Mark Throndson and Sudhakar, thank you very much for your time.
Thank you.
Thank you.